All right. Good afternoon, everyone, and welcome to this Washington Statistical Society virtual seminar. My name is Katherine Irimata, and I'm the current WSS Methodology Program Chair, and I'm chairing this presentation. And Ching Pan is also here assisting and is also on the WSS board. So today we'll be hearing a talk from Dr. Phil Kott on two not so different approaches for dealing with not missing at random unit non-response. And then afterwards, we'll have some time for questions. If you have questions during the presentation, you can submit them in the chat, or at the end, you can raise your hand and we can unmute you so you can ask any questions. So I'm pleased to introduce our speaker, Dr. Phil Kott. Phil learned survey statistics working for BLS, EIA, NAS, the Census Bureau, and again at NAS, where he rose to be its chief research statistician. For his statistical contributions at NAS, he was inducted into the Hall of Fame. Phil is currently retired from federal service and working part-time for RTI International. He received his PhD in economics from Brown University in 1979. His background in economics exposed him to both the usefulness and folly of assuming simple mathematical models, which has served him well in his 40-plus years as a survey statistician. He's a past president of the WSS, a fellow of the American Statistical Association, and a past chair of its survey research methods section. So Phil, thank you so much for being here, and I'll turn it over to you.
Okay, thank you. Am I supposed to, so I can see the screen hit this? I hope so. Hope it doesn't disappear. Okay, so I got to figure out where to get the faces out of the way so I can see this. Okay, so there's the title, as Katherine said. And the two not so different approaches are calibration weighting, which is what we champion at RTI with our SUDAAN software, and pattern mixture modeling. And you'll hear a lot more about the first and the second, but we'll hear about the second towards the end and in the discussion. Why isn't this going down? I hit page down, isn't it the right thing? And not moving. Why isn't it moving?
Use the arrows on your keyboard instead. There you go.
Oh, no, page down work. Okay, first I'll talk about developing my favorite, what I call my favorite equation. Then I'll talk about the outcome or prediction model under ignorable non-response. Then the response or quasi model with missingness at random. And then I'll switch that to the response model with missingness not at random. And the movement from one to the other is so quick, if you blink, you might miss it. In fact, when I explained it to a couple of people, sometimes they said, so what's the difference? And hopefully in my presentation, you'll see the difference. Then I'll talk about the outcome model, not ignorable non-response, which is a little harder to get your arms around. And then the pattern mixture model, which is very similar to the outcome model, in fact, it is the outcome model with not ignorable non-response. And the big difference between pattern mixture modeling and calibration is pattern mixture model concentrates on the outcome model, while calibration concentrates on the response model, but the results are very similar. And then there'll be some discussion. And I don't have that many slides, but I might blather long enough to take up the time. Okay, so let's start with my favorite equation, bias from non-response on the simple random sampling. Almost everybody has seen this formula. And I always forget when I point things to with my cursor, nobody can actually see it. So bias is the bias for a simple random sample where there's ignorable non-response. We usually say the sample mean. The bias is the difference between the sample mean and the respondent mean and the full sample mean. So it's a bias in respect to the full sample mean. And so we have a difference, and then I write it the second way. Capital RK is 1 if he responds and 0 if he doesn't respond. So the second equation is really just the same as the first, reformulated a little bit. You can reformulate a little bit by subtracting off a mean, and you can subtract off a mean because this whole thing, the first part just sort of sums to 1. So you can subtract off any old thing. And you can rewrite it this way. And what's interesting about this is it basically says, well, you have no bias if either one of two things happen. If either all the y's have the same mean, there's going to be no bias. Or if the probabilities of response are all equal probability of response or equal to the fraction of respondents. So if either one of those two things are true, then there's no bias. Now we can add weights. Now I'm going to say the weights are D. D is either 1 over the probability of selection for totals or 1 over the probability of selection over the sums of 1 over the probabilities of selection for the whole sample for means. I just call that the sample weight. And mostly we'll be thinking about means, although I'll give you an example with totals, which is the example that I was working with a lot for. So if you do it with weights, do sort of the same thing. This is the way that we don't. I have E tilde R because this could be the probability of response, or it might not be. It might just be a bad guess at the probability of response. So if it's a bad guess, there'll be bias. If it's a good guess, there won't be bias. This is sort of what you'd have for among the respondents, and this is what you'd have in the sample, and the bias sort of rearranging term sort of looks like this, which is a long way from this because I don't have a subtracting off the mean at the end. But it turns out I have better than subtracting off the mean. I can subtract off any multiple of a vector z, as long as this sort of guess as to what the probability of response is, as I'll call G, as long as it sort of satisfies this equation, sort of the weighted average of the z's with the probability weight for the respondents with this g's here is equal to the sample total for these z's, and that's called the calibration equation. So as long as the calibration equation holds, for any g that solves the calibration equation, this equation is an equation for the bias. So in summary, the bias now looks like this, which is very similar to what it did before with weights. And we have either two possibilities. There's no bias if the expected value of y is this linear function of the z's, or, and that's true among anybody who responds or doesn't respond, or if the probability of responses are correctly modeled this way. So if either one of those things are true, we're unbiased in some sense. And that's sometimes called double robustness, which I don't like, or double protection, which I prefer, but I've sort of given up. I'm going to posit a little example because I'm going to have a lot of x's and z's and y's floating around. Sometimes it's helpful to think in terms of a real sample. So suppose yk is the current annual number of drug-related visits to emergency departments, which I'm going to call k. And it's a function of a vector z, and the first 4 components of z are just dummies for the 4 regions of the country, and the 5th one is the number of visits to emergency departments in a frame year. Now we're interested in drug-related visits, but this is all types of visits. And we're going to say, y is perhaps a linear function of these things. Maybe it isn't, maybe it is. Who knows? But we're going to sort of think in terms of what our z vector is. And the interesting thing about the z vector is it doesn't contain an intercept, except if you just take a linear combination of the first 4 with like ones in front of all of them, it sort of turns into an intercept. So although we don't have an intercept, this is the equivalent of having an intercept. And I'll talk about the notion of the equivalent of having an intercept again in the talk. So let's firm up a little bit of the mathematics. The estimator, which is a D, and we're only going to count response. So it's a sum of the entire sample of counting just the people who respond. Remember, RK is 1 for respondents and 0 for not, times this G, which satisfies the calibration equation, and a Y. It's nearly unbiased in some sense if the outcome model with ignorable non-response, which is this is the outcome model. Y is a linear function of z plus an error term. If the expected value of z is 0 for everybody in the sample, given z and given respondents. So basically, ignorable non-response means the same model for respondents and non-respondents. And g can be any function of z that satisfies the calibration equation, but except it can't be a function of y given z. That's what ignorable non-response means. It can't be a function of y given z. It can be a function of z, but not of y given z. So it can be a function of the regions and the frame emergency department visits, but not the current drug-related emergency department visits. I'll say EDs in the future. I probably forget about the example entirely. Now, one version of G that's quite popular is this ugly mess. It's 1 plus a linear combination of the Z's, where this is a linear combination. Now, I won't expect you to memorize it. It's an ugly mess. I'll agree. If you plug it into G, it looks like this. And if you plug it into T, our estimator, it sort of looks like this, which is sort of like a regression equation, regression estimator. The bias is the difference between, for the Z's, for the whole sample, the respondent sample has to be fixed by something. And it's fixed by something that looks very much like a regression estimator among the respondents of Y regressed on the Z's. And in fact, if the Z vector, and as it does in our case, contains one of the equivalent, it doesn't contain an intercept, but it contains the equivalent of an intercept, because if you add up the first 4 regions, dummies, one of them is going to be 1, so that's fine. They'll have this form, which is sort of like a total, an estimated total for the Z's, which we know. We're assuming that's known for everybody in the sample, times this regression coefficient, this B here. And if that's true, again, we're unbiased on the outcome model under ignorable non-response. Now, the estimator is also nearly unbiased in some sense. If the expected value of response, or the probability of response, because response is 0, 1, so its expected value is the probability, is 1 over some gamma function of some x, can be consistently estimated by some g function. What's all this stuff mean? Well, in our case, this g function looks sort of like this, 1 plus lambda z. Well, that's saying that the inverse of the probability of response is a linear function of the z's. But that's a dopey response model. But that's the response model under which what we posited before, this regression estimator, this linear regression estimator, is unbiased. A much better G would be 1 plus e to the gamma plus z, where G satisfies the calibration equation. And that would be logistic response. So if non-response or response is a logistic function of the Z's, celebrated calibration equation, then this would be unbiased under the response model. Remember, if the G celebrates the calibration equation, it's unbiased under the output model. If it celebrates the response model, it's unbiased under the response model. If it satisfies just one and not both, it's unbiased in some sense, which is why we call it double robustness or double protection. Now, remember I said gamma is a function of x, and then quickly I made it z again. Well, it doesn't have to be. Oh. Suppose it's logistic function of some x, where the components of x are the same size as the component of z's, but some component of x's, if all the x's were functions of z's but not of y of z's, then it would be missing at random. If some of these x's were functions of y given z's, then missingness is not at random. So long as the dimension of x and z are the same, and g follows the calibration equation, which is in z's, then then the logistic function of the x is unbiased in some sense. So we went from missing at random to missing not at random by just changing x to z and saying, just changing z to x and just saying x can be a function of y. So for example, in our example, if we replace z by an x, which is the same 4 regions, but instead of saying non-response is a function of annual emergency department visits in a frame year, say non-response is a function of actual drug-related emergency department visits in the survey year, which is actually what we're trying to measure. So we can actually stick what we're trying to measure in the x function, and solving the calibration equation, we can say we're adjusting for missing not at random. Now, it's also true under the outcome model, where the outcome model looks like the same outcome model before, except we're saying the expected that for everybody in the sample, the expected value given X is 0 and R, where X can have Y as one of its components, as in my example. The output model, we would just say, well, what's the expected value in the output model? And instead of Y, we put in ZB plus epsilon. Well, because of the calibration equation holding, this first part is equal to this first part here, and the second part is equal to the second part here. And because we're saying the expected value of epsilon given X and R is 0, the second part is 0. And so we just have the first part. And you don't have, when you, under the output model, you don't have unbiasedness. What you have is unbiased predictor, which means it predicts the same thing as the weighted sample itself. So it predicts the same thing as this. So under the outcome model, it's true. So we still have the same sort of double robustness as we had before. Now, in particular, G can be our old linear friend, except with Z replaced by X. And if you do that, you plug everything in, it's exactly the same before, except instead of this looking like instead of the B's looking like a regular regression with the respondents, it looks like an instrumental variable regression, but with the X's serving as the instruments and the Z's turning as the model variables. But in fact, our things are sort of reversed, because we're estimating, well, when we did the fitting through the non-response model, the X's were the model variables and the Z's were sort of instrumental. Here, in terms of what it looks like, in terms of the regression, it looks like it's the other way around. And in fact, well, I'll talk about the cases because it's the simplest to deal with, where X and Z had the same dimensions. In real life, in instrumental variables, you can have more X's than Z's, but in our case, you can have more Z's than X's, but we'll just talk about cases when X's are equal to Z's. Well, I just talked about cases where X is equal to Z's, and they look exactly the same. Now, so that's the calibration approach. What's the pattern mixture modeling approach? Well, the pattern mixture modeling approach, recall that we said the bias can either come from the outcome model being incorrect or the response model being correct. We focused with not ignorable non-response and the response model, where response is now a function of X rather than Z. We had this outcome model reports, but it wasn't quite satisfying because saying epsilon is not a function of X, which really doesn't sound quite kosher. What they do in pattern mixture model, they say, well, first, let's say we just ran a simple regression of the Y's on the Z's and just fit it and call that YK hat. A pattern one is the usual thing. If non-response is a function of Y hat, but not of Y given Y hat, we can just do our normal regression. Whether we use weights or not is a matter of taste. Now, if non-response is a function of Y, but not Y hat, then we can do something like instrument variable regression. Or we can have a combination of the two. And in SUDAAN and ease, like we say in calibration, we're just saying the Z variable is 1 over Y hat, and the X value is 1, and some linear combination of these two. Now, in one hand, we've got pattern 1, and the other hand, we have pattern 2. When it's some linear combination, we have a mixture. And in pattern mixture modeling, they talk about they have some fancy-dancy Bayesian way of deciding what to do, which turns out to be just halfway between the two. But in real life, I would say that, well, take a step back. Now, why are we saying that non-response can either be a function of Y or can be a function of the model fit of Y, the regression model fit of Y? Well, because anything else, at least according to people who believe in outcome modeling, anything else is irrelevant. Because the only thing that matters is what controls Y and what controls response on Y, because we're trying to estimate Y. So if we're trying to estimate the mean or total of Y, the only things that can affect, the only thing non-response can affect is either Y itself or what y is made of. If y it can be fit perfectly by z, if y is a perfect linear function of z, it doesn't matter which way you fit it. All the estimates are the same. It's only when y is not a perfect function of z that we have the possibility that non-response can be a function of y, it can be a function of the fit of y, it can be somewhere in between. The way I like to think of it is the usual way of doing things is not ignorable, is ignorable non-response. You do that fit, and then you do the other fit, assuming we're putting y in place of a y hat, and you have the upper bound of what the bias could be if non-response was in fact fully not ignorable. There's no way, or there used to be no way of telling whether things are ignorable or not ignorable. There's a new way that's coming out using randomized response. Michael Bailey has a paper on that. He hasn't published it anywhere. He's talked about it. There are more complicated papers written in the non-survey statistics literature that we really have to wait for Michael Bailey's paper to come out for it to make any sense to us. But anyway. By the way, if anybody's raising their hand, I cannot see. Oh, yeah, I see chat. I don't see hand raised. Okay.
No hands raised yet. You can continue.
No hands raised. Okay. So the output modeling approach, which is the key of pattern mixture modeling, because we're only interested in a y, you can only have a single survey variable. In real life, you have multiple survey values. That's the reason why one of the reasons we like using weights, and that's one of the reasons we like calibrating through a response model, because for unit response at least, it's the same model for everybody. Here we need a separate model for everybody if you want to just do outcome modeling and you want to have more sophisticated output modeling and the possibility that different y's are functions of different z's. And if you want to do domains, for example, you need a whole different model. But with response modeling, you don't have to do that. Now, in the pattern mixture literature, they start out with not just a linear model, but with a linear normal model. Well, fortunately, when I took the regression for the first time, I was in, as Katherine said, my PhD is in economics. And when I took linear regression, I took it in an econometrics class. And they were supposed to teach us about statistics before, but they never did. So I never learned about the normal model, or at least I learned about linear regressions without a normal model. So to me, it was just a fit. So I don't think in terms of normal models. Also because I'm an economist, I know data is never normal. But a lot of times we deal with surveys of binary variables and where it fits more sense to find a logistic model or a probit model. Well, if you believe in normal distributions, or if you're an expert in normal distributions, natural thing to go to is probit. And of course, that's what they do in pattern mixture models, is they go from the normal continuous model to a probit binary model or a multivariate model. What I suggest to do is, if you just have a low nonlinear model, why not just replace z by 1 plus the fitted? And remember, like in the case of linear models, we don't even worry about what all those z's are. We don't worry about non-response being a function of something other than the y's, because the only thing that matters is y and what fits the y, because we're trying to just fit y. So we can just put 1 over y hat and make that z, and then, oh, I was supposed to have more. I think I erased it. Oh, well. And you can have x can be then 1 over y fitted, if you want to say ignorable non-response. You want the possibility of not ignorable non-response, you can make x 1 over y and see how much bias that could cause if in fact model is not ignorable. And you can't really tell again if the model is ignorable or not ignorable without a randomized response mechanism. There's actually a proof that you can't tell the difference between you can't, with the data at hand, tell if a model is ignorable or not ignorable, because the ignorable model will always fit better than the not ignorable model. Doesn't mean it's right, it just means it'll fit better. Sometimes it's nonsensical to say there's not ignorable non-response. the classic case is income. Whether a person reports his income or not is usually a function of how much income he has. It's not a function of what income is fit on. It's what income itself. So you can say, well, the fit is better if I fit income, but we know that in fact it makes much more sense to say non-response is not ignorable rather than ignorable. Now, SUDAAN, I talked before about logistic function, fit up a slight expansion of logistic regression. It will allow your weights to be bounded by something other than 1 and infinity. It can be a little higher than 1, or your weights can go between 1 and infinity. They can be bounded. The upper bound of the weights at u and something less than infinity, and the lower bound at something greater than 1. Unfortunately, there's no way of telling what u and l is. You've got to fit several things and decide which is best for your data. Generally, you try to make u as low as you can get away with and still have the calibration equation fit. That's generally what we do. There's something else here. Now, often when you have calibration variables, for means or totals, you can either have some data for the entire population and some data for the sample. SUDAAN can handle both, but not at the same time. Either one or the other, but not at the same time. There's probably a way to do both at the same time. I just haven't figured out how to do it, how to cheat it yet to do that. Now, one thing comes out of all of this that is something somewhat interesting is what's the purpose of design weights in the first place? Now, the pattern mixture people generally don't like design weights at all. Remember, there was no design weight at all in their fitting when they made the Y hat. And the weights only make sense. Design weights are actually just like our 1 over R functions. The only difference is you don't have to estimate them from the data. We know what they are from the sample design. And their purpose is that if they are a function of Y that we don't even know about, they account for essentially non-ignorable sampling. We call that, I forgot what we call it. Alzheimer's disease. What is the word for it? Informative. We call that informative sample. Informative sampling is sort of the same as non-ignorable sampling. So if the sampling is not ignorable, you've got to put weights in because we don't know if the sampling is related to the Y's, and we stick these in to hope it fixes it. Just like in calibration, we stick 1 over Rx to hope to fix response. We fix sampling by sticking weights in, these in. Okay, that's what I'm not going to talk about. Okay. And finally, I'm going to offer some reading. Remember, you may have noticed I haven't referenced anything in this paper other than saying that there are people who do this pattern mixture. They're in some weird place, like Michigan or so. One paper that I kind of like that I didn't talk about at all is the RGO and Skinner. It's a paper in survey methodology, and it has almost nothing to do with the subject. But what's interesting about it is they were looking at calibration for non-response, and they were looking essentially at 2 types of calibration. The calibration that assumes non-response is 1 over a linear function of z's, so they can just use linear calibration, like the normal regression, the normal Gregg estimator. Or it might be a raking type model, which is a multiplicative value. So it's sort of the SUDAAN formula. It's the SUDAAN formula with, here's my SUDAAN formula, with a lower bound of 0 and an upper bound of infinity, or just e to the x, e to the multiple of x, or e to the multiple of z's. This was ignorable non-response, so it was z's. Where am I? Yeah, I go in Skinner. And they looked at those 2 things. They actually looked at a 3rd type of calibration, which is sort of equivalent to what empirical likelihood would give you. And they found out that no matter how they did the non-response, if they did the non-response either assuming a raking model where non-response, where the log of non-response was a linear function of the covariate, some covariates, or if it was a linear 1 over a linear function, whichever way they did it, the bias is about the same. however they fit it. It really didn't matter that they fit the wrong response model. It still tended to remove the bias. And it tended to remove the bias of an estimate of the unemployment, of how many people are unemployed, given we know the population size. So it's a binary function. It's not a linear function. They fit it with a linear calibration. So the response model was wrong, the output model was wrong, outcome model was wrong, and still they seem to remove the bias. So that's a pretty interesting result. So what it seems to say is models don't matter. They just approximate reality, and it's good enough, at least for surveys. That was something to point out. Another thing is, if you want to actually read about proxy, what I call pattern mixture models, they sometimes call it proxy pattern mixture models, which I find tongue twisting, so I leave out the proxy a lot. It's a good survey, good article, the first article in the survey literature that I know of by Andridge and Little. Little is the first champion of that. And that's here in the Journal of Statistics. These are two papers, not by me. You can't see the heading because there's something in the way. I don't know if it's the way to you, but it's the way of mine. I can't see the heading. It says two papers, not by me. And then there's one paper by me, which is a paper I wrote with Dan Lau. It's in the Journal of Survey Statistics and Methodology. It talks about the theory behind this, when there could be more calibration variables than response model variables. And one of the things I discovered is that what I was trying to fit is a model with non-response was only a function of the y variable. So I used sort of a y and a y hat. And it turned out, not using the weights and not using the g's at all, and fitting the y's, and then sticking that into the equation was just as good as a fancy dancy approach to try to fit the response model, in which case you stick in an R, you don't even stick in a G, you stick in the derivative of G's for reasons that are obscure I won't mention to you. That's what the response model should say if you knew what the response model was. And I knew what the response model was, and I put it in, and it worked no better than just fitting it with ordinary least squares on the respondents. Again, not for calculating the calibration itself, but for the step before the calibration, which is to find the y hat to stick in the z, or to stick in the x. So it's one in the y hat in the z, and one in the y in the x, if you're assuming completely non-ignorable non-response, which of course we had because we did a simulation that had non-ignorable non-response, and we found out that the bad fit from response model point of view, from an output model point of view, who cares? We don't care about the response model. We only care about the outcome model. It worked out perfectly well. So it's a disappointing result because this is the other guy was right and I was wrong, but that's what it seemed to say. And that's all I have to say. I talk too fast. I blathered a little, but I talk too fast. So does anybody have questions? Is anybody still awake? That's the trouble when you don't have an audience in front of you. You can't see any of this stuff.
We're still here. Thank you so much, Phil. Yeah, that was a great presentation. We can open it up for questions now. I think you may not be able to unmute yourself, but if you raise your hand, we can unmute you, or you can type your question in the chat. While we're waiting for people to submit questions, Phil, I had a question. So
okay,
for calibration, you're specifically in your abstract, you mentioned suggesting SUDAAN's weight adjust X.
Mm-hmm.
There a reason why you would recommend this procedure for calibration? Does that make it more similar to the pattern mixture model, or is it just general calibration approaches? Well,
first of all, there aren't many ways to do non-ignorable calibration. Lumley has a package that does it in R. There's another package I think will do it in R, but won't give you standard errors at all. Lumley gives you what I think is the wrong standard error formula under the response model, but as I said before, it really might not matter. He basically gives you variance estimated under the outcome model, but not under. See, I would like it to be both under the response and the outcome model. This is really only unbiased under the outcome model, theoretically, but it might not matter. You know, you might not know this, but Sarndal and forgot his co-author. It also begins with an L. Have a whole book on fitting models, and they basically, well, it doesn't matter that a response model is wrong. Our variance estimators work, and his variance estimator is completely wrong from the response model he uses, which is 1 over the linear function. His variance estimator is completely wrong, but it works out okay because his outcome model isn't bad. Even though he doesn't believe in outcome models anymore, he only believes in response models and probability models. And even though he knows there's no proof that his variance estimator should work, it basically works because the outcome model works. And the outcome model works even if the outcome model is incorrect, as we found out in Diageo and Skinner's paper. Even though we know the outcome, it really should be a logistic model, not a linear model. They're fitting it with the linear model, it still works. And that's what happens in, I want to say Lumley, but certainly it's not Lumley, in the Sarndal's book on non-response. He has a paper. They have a paper together. They also have a book on fitting non-response models with calibration. Okay. Again, it's all linear calibration. Even though, as you said, the response model is silly, but it works. So who cares?
Thanks. And then you talked a lot about the similarities between the two, but is there a reason why we would choose one approach over the other? What are the
again, the advantage of the outcome model approach, as far as I can tell, is that the outcome model approach seems to be what wins the day in the sense of a lot of things that the response model wants to do, you don't really have to do. The reason why I prefer the response model is the same reason we weight the data, because we're not trying to estimate one thing. You know, pattern mixture model is great if you're only trying to estimate one thing. I don't know how many of you run surveys that try to estimate one thing. We're usually trying to estimate a lot of things. And that's why we like weights. And that's why I like calibration weights. In principle, they have calibration weights too. They don't call them calibration weights, but they're the inverse linear calibration weights. But it's a different one for every y variable you want, as opposed to the same one. So there's a lot of practical reasons to want the same one. There's a lot of theoretical reasons why we shouldn't worry about the response model. We should only worry about the outcome model. But there's a lot of practical reasons we should only worry about the response model, because again, one weight is so much better than a different weight for every y.
Yeah, it does help generalize. There's a question. I have a question in the chat. Can the approach be applied to non-probability based surveys using pseudo weights?
I would make the pseudo. I don't like the pseudo weight approach. You can make the pseudo weights this way, and that's what I do. Right? You can just say, let's cause the weight. Let's make weights that satisfy the calibration equations. So you might start out with weights of 1, and then force the calibration equation to be equal. Now, in SUDAAN, there's a problem with that. It's a bug in the program, in a sense, in that if you start out with weights of 1 and the real weight's supposed to be 1,000 because your sample is only so small and your population is so much larger, it won't find the solution. So you've got to trick it to find the solution by starting out with like a number greater than 1. But it can be done, and that's the way I would do it. And I actually have a paper on that, which is in the proceedings in 21. It will be in RTI Press eventually, as soon as I get my co-author. So, as some of you know, heard me before, I got a lot of great ideas, but I'm a terrible programmer. So I have somebody else programming all this non-probability sampling stuff for me, and so we wrote the paper, and they want an appendix with some of her SUDAAN code, an explanation of what the SUDAAN code does, but she hasn't written it yet. So as soon as she writes it, it'll be RTI Press. Right now, you'll have to read the proceedings version, or ask me for a copy, which has a lot of the errors corrected. But again, I don't have the SUDAAN code in it yet.
Okay, thanks, Phil. And thanks, Ben May, for your question. Phil, I do have another question. So you mentioned, I understand the reasoning for preferring a response model over the outcome model. I'm wondering practically, like you started the talk giving an example of how we might think about this. Is this something that you've looked at, like using the calibration approach for a response model compared to several pattern mixture models for the outcome models to see practically if they look similar?
Well, again, I didn't use pattern mixture model per se,
Okay.
except I did use their Y hat. And in fact, so it's in the paper I said, so I did use this Y hat, a simple regression without weights, without D weights, and in fact, it's not G weights, but it's a G prime weight, which the response model says to use. And it turned out, in most cases, the mean squared error was better my way. The bias was better the pure model way, the pure outcome model way. Now, again, I didn't use pattern mixture model in the sense of I compromised between response and non-response. In this, I copied ignorable and non-ignorable. In this case, I knew the non-response was not ignorable, so I was looking at the extreme. So the extreme, in terms of bias, actually worked better using the pattern mixture modeling approach than the response modeling approach for this one empirical example.
Okay, thanks. Any other questions from the audience? You can either raise your hand to be unmuted or type your question in the chat. All right. I'm not seeing anything, so I think we can wrap up the presentation today. Phil, thank you so much for giving the presentation, and thank you all for attending. This presentation was recorded and it will be posted on our WSS YouTube channel. We have an upcoming presentation scheduled in January, on January 29th with Dr. Wei-Yin Lo. So please keep an eye out for that. There'll be an announcement going out and more information posted on the website. If you have suggestions for ideas, topics, or presenters for upcoming seminars, please email me. I just put my email in the chat. Upcoming seminars, as I said, there'll be email announcements coming up, and you can always check the website. So thank you so much for attending, and happy holidays, everyone. Thank you, Phil.
Yeah, happy holidays. Take care. Bye.